All right, welcome everybody. I wanted to describe the min-cut problem in linear programming, and then afterwards we'll show how it dualizes maximum flow. So in the min-cut problem, we're taking the dual perspective, okay? So we're an enemy of the ski resort. We have all these chair lifts, and the capacity of each edge tells you how many people can flow from along that chairlift per minute. Okay, we want to come in the middle of the night, we want to selectively destroy some of these chairlifts so that it's impossible for for the ski resort to open tomorrow. I guess we're the competing ski resort. And how expensive is it to sort of damage a ski lift? Well, it costs more to disable a ski lift depending on how big it is. So this ski lift that can take 50 people per minute, it'll take us $50 to disable. Whereas this ski lift that can only carry 20 people per minute, it'll only cost us $20, say, to disable this ski lift. So what we're trying to do is we're trying to find a way to sort of like disable a collection of ski lifts so that now it's impossible for anybody to get from the bottom of the mountain to the top of the mountain. Okay, so we'll cut some group of ski lifts, like maybe these. What's cool is that the maximum flow, the number of people that can get to the top of the mountain, is always equal to the minimum cut, the expense you have to pay to separate the bottom from the top or the source from the sink. You can see that on this particular problem. We saw in the last video how the maximum flow here was 60, and the minimum cut is also 60. You could cut right here to have a cut that only costs you $60, or you could cut right here, for example, to have a cut that only costs you $60, and that separates the bottom of the mountain from the top. So instead of just writing down a linear programming problem that solves min-cut, I'm going to take the linear programming problem we saw that solved maximum flow, dualize it, and then massage it until we get a minimum cut problem. So if you remember the maximum flow problem, our linear programming problem was maximize C transpose X subject to AX is at most B, or X is non-negative. X was this vector of flows along each edge. And the first entry of this vector was the flow throughout the entire network, meaning the flow leaving the source or equivalently coming in to the sink. So when we're maximizing C transpose X, I just take this product and I get F. We're trying to maximize the flow. And then we had constraints, one for each vertex, V1 up through Vn, and then an additional constraint for each edge. The constraint for each vertex said that, well, my variables are indexed by F and my edges. And then each edge column had a 1 and a -1 for the vertex it sort of left and came into. And so if you pay attention to a particular vertex, I have a bunch of 1s and -1s depending all the edges that are coming in and out. So each vertex constraint says that the flow leaving that vertex is at most the flow coming in. So matrix A times vector X is going to be at most 0 in that entry to say that the flow leaving is at most the flow coming in. The second part of this matrix in this bottom right corner is just going to be the identity matrix. And that's so that when I multiply A times X, so when I multiply this by my vector X, I just get out, variable Xij is at most Cij, the capacity of that edge. So each edge constraint tells me that my flow along that edge is at most the capacity. So let's just write down the dual of this problem. maximize C transpose X subject to AX is at most B with X non-negative becomes minimum B transpose Y subject to A transpose Y is at least C and Y is again non-negative. All right. So here was matrix A, and I've just transposed it. Okay. So the column in A corresponding to the flow F now becomes a row in A transpose corresponding to the flow F. And the columns in A corresponding to each edge became rows in A transpose corresponding to each edge. The rows in A corresponding to each vertex constraint become columns corresponding to each vertex. And the rows in A corresponding to each edge become additional columns corresponding to our edges. So you'll notice that the columns of A are sort of split into two, sorry, the columns of A transpose are split into two types. We have the vertex columns of A transpose coming from our vertex constraints. And we have our edge columns of A transpose coming from the edge constraints in maximum flow. That means that our variable vector Y really has two different types of entries, right? Because I'm going to multiply my variable vector Y by A transpose. So some of my variables are going to encode things about vertices because they're going to get multiplied by these vertex columns. And some of my variables in Y are going to correspond to edges, things about edges, because they're going to be multiplied by these edge columns. All right. So let's call my variables Y, let's call them U1 up through UN, where N is the number of edges. Okay. And let's call them Yij, where I have one variable Yij for each. Sorry, I misspoke. Let's call my variable vector Y U1 up to UN, where N is the number of vertices, and then Yij, one Yij variable for each edge. All right. A transpose Y should be at least C, which was previously my optimization vector, but is now sort of my constraint vector. And I'm trying to maximize B transpose Y. B was previously my constraint vector, but now in the dual, it becomes the direction I'm trying to optimize. So it has all the capacities encoded in it. All right, so in this bottom left part of matrix A transpose, I encode the incidence between edges and vertices. So I have a 1 and a -1 for each edge, corresponding to the vertex I come into and leave out of. So this has 1, 1, and -1 per row. In the bottom left portion of matrix A transpose. On Thursday, we'll use that to prove that this matrix is totally unimodular. Okay, so far I've dualized maximum flow just in terms of matrices. Let's transport this matrix equation into actual equations. So I'm trying to minimize B transpose Y. All these zeros give me nothing regarding the U variables corresponding to vertices, but all theseCij's give me terms of the form Cij, Yij. So I have the capacity of an edge multiplied by these variables corresponding to edges. That's what I'm trying to minimize. Subject to, this first row is interesting. When I multiply this first row by this vector, I get negative u1 plus un. Do you see that? So this first row gives me negative u1 plus un, has to be at least 1. Okay. Every other row, okay, on the left part of this row, I have a single 1 and negative 1 corresponding to the incident vertices to each edge. And then on the right part of this row, I have a single 1, just corresponding to which edge I'm looking at, edge ij. So that gives me equations of the form ui minus uij, so ui minus uij, plus yij is at least 0, non-negative. I'll reinterpret that for you in a moment. And then, since my vector of variables is non-negative, that tells me that the ui's are non-negative and the yij's are non-negative. Okay. What we're going to see is we're going to use total unimodularity to see that we could furthermore assume that these variables can be integers without changing the optimum. And furthermore, we're going to see that these variables can all be either 0 or 1 without changing the optimum. So actually, we'll see that ui can always be taken in an optimum solution to be 0 or 1. And same for yij. So we'll furthermore see that ui is either 0 or 1, and yij is either 0 or 1. This will allow us to recast this problem as min-cut. And I'll say this again later, but let me say it briefly now. All right, so the vertices have labels ui. Some of the vertices are going to have label 0. And other vertices are going to have the label 1. Okay. These are going to be the two sets that are separated by our cut. So our cut is going to go through something like that, separating the vertices labeled 0 from the vertices labeled 1. So believe me for a second that all the ui's have to be 0, 1, and same with all the yij's. Okay, this constraint is telling you that u1 has to be 0 and un has to be 1. Okay, so this constraint right here is telling me that furthermore, I have to have the source in the set of all vertices labeled 0, and I have to have the sink in the set of all vertices labeled 1. Okay, yij, I'll draw the yij's in red. Yij is going to be 0 between, so if an edge goes between vertices of the same set, then it's going to be 0. But yij is going to be 1 if it goes between vertices in different sets, if it's one of the ski lifts that we have to cut. All right, so that is told to us by this equation, okay? If ui and yi are the same, if they're both 0 or both 1, you can take yij to be 0, right? If both ui and uj are the same, if they're both 0, you can take yij to be 0. If uij corresponds to an edge going backwards, if it's going from 1 to 0, if it's 1 minus 0, you can again take yij to be 0. But if ij is an edge going from the vertices labeled 0 to the vertices labeled 1, right? If this is 0 minus 1, then you better have yij be at least 1 to get back to non-negative, right? So if we have 0 minus 1, Yij better be 1. So I'll say this again in a moment, but the ui's are going to be 0 or 1, telling us which vertices are on one half of the cut versus the other. And then the yij's are going to be 1 only if they're an edge we need to cut, like there. And so we are minimizing the sum of capacities along the edges we've decided to cut. Questions so far? Alrighty. Let me back up some of these unsubstantiated claims a little bit. We'll see on Thursday that this matrix is totally unimodular, okay, meaning that any square submatrix has determinant 1, -1, or 0. And then the main theorem about totally unimodular matrices is that if you have an optimization problem with a totally unimodular constraint matrix, and your constraint vector is also integral, then you don't change the optimum by asking for integer solutions. So this constraint vector is integral. So we can add these constraints that I want ui's and yij's to be integers without changing the optimal solution. Furthermore, in an optimal solution, we can always take the ui's to be either 0 or 1, right? This is telling us that u1 and un have to differ by at least 1, okay? But besides that, you sort of want the ui's and uj's to differ by as little as possible, because if ui and uj differ by more than 1, you're just saying that yij's have to be bigger, but we're trying to minimize something in terms of the yij's. Okay, so in an optimum solution, you can always take the ui's to differ by at most 1. So for simplicity, you might as well take them to be 0 and 1. And then look at this equation. Ui minus uj plus yij is non-negative. If ui and uj are equal, or if ui is bigger than uj, you might as well take yij to be 0 in an optimum solution, because you can and still satisfy this constraint and all the others, and you're trying to minimize something in terms of yij. But if ui is 0 and if uj is 1, then you need to take yij to be 1 to get back to non-negativity in this constraint. So when I write down the same optimization problem, but constrain the variables to be 0 or 1, I get the following. Minimize the sum of capacities for the edges we cut, subject to the source vertex and the sink vertex have to be in different halves of the cut. If I'm cutting between the vertices labeled 0 and the vertices labeled 1, I have to have yij equal to 1. Otherwise, it's 0. And all my variables are now either 0 or 1. And this, as I've described already, divides the network into 2 sets. I have a set of vertices labeled 0, which includes necessarily the source. I have a set of vertices labeled 1, which includes necessarily the sink. So these vertices on the left are in my vertex set V0. The vertices on the right are in my vertex set V1. And then yij is 1 if it's separating between those 2 sets. So on these edges, yij is going to equal to 1. On all other edges, yij is going to equal 0. And so we're minimizing the sum of capacities just of the edges we need to cut to separate our 2 halves of vertices. So this is a nice overview why the dual linear programming problem of max flow is indeed min-cut. There are other explanations not relying on totally unimodular matrices, but our matrix today relied on that. And what remains is to show that our matrix is indeed totally unimodular, as I'll explain next time. What questions do you all have? All right, thanks.